F block elements. These elements are present below the periodic table as two series, the lanthanoid series and actinoid series. Lanthanoid series is the 4f series, that is, in these elements 4f orbital is filled from 1 to 14, and similarly in actinoid series 5f orbital is filled from 1 to 14. These elements are also known as inner transition elements because of their position in between the transition elements, that is the D block elements. You can see here the lanthanum and actinium. These are the elements of D block. After lanthanum there is lanthanide series from cerium to lutetium. From cerium to lutetium, that is atomic number 58 to atomic number 71. Similarly, after actinium we have actinide series, that is from thorium to lawrencium. So these are the two series of inner transition elements, and this shows the position in the periodic table. Then the general configuration we have already studied. General configuration of F block elements is n-2 F1 to 14. Here you can see n-2 F1 to 14, n-1 D0 or 1, and n is 2. All the general configurations are shown over here, the S block, D block and P block. But here we are studying F block elements, so the configuration is again n-2 F1 to 14, n-1 D0 or 1, and n is 2. This you have to remember. For lanthanoids, the value of n is 6. So the general configuration becomes 4f1 to 14, 5d0 or 1, and 6s2. Similarly, for actinoids, the value of n is 7. So the general configuration will be 5f1 to 14, 6d0 or 1, 7s2. Then the important topic in this is lanthanoid contraction. The steady decrease in the size of lanthanoid atoms and ions with the increase in atomic number is called lanthanoid contraction. You can see here the size of atom goes on decreasing from lanthanum to lutetium, and the reason for this is poor shielding effect of F electrons. These are the radii of ions of lanthanoid series from lanthanum to lutetium. These are the 3+ ion. You can see the gradation, the decrease in size. Then cause of lanthanoid contraction, as told, the additional electron enters into n-2 f orbital, and this f orbital has a poor shielding effect due to its diffused shape, and because of this the effective nuclear charge increases with increase in atomic number, and outer electrons are attracted more by the nucleus. So radii decreases from lanthanum to lutetium. Now this contraction also occurs in actinoids. The difference is that here the contraction is more. That is, the jump in contraction between the consecutive elements in actinoids is greater than that in lanthanoids. It is because of the reason that 5f electrons have even more poor shielding effect. Consequences of lanthanoid contraction. There are three main consequences. The separation of lanthanoids become easier, then basic strength of hydroxides decreases, then similarity of second and third transition series, that is 4D and 5D series. Let's take these one by one. First consequence is separation of lanthanoids become possible. See, otherwise the lanthanoids are very much similar that they are extracted all together. But because of lanthanoid contraction, they slightly vary in size, and this property can be utilized to separate them by using ion exchange method. Then another consequence is decrease in basic strength of hydroxides from lanthanum to lutetium hydroxide. As the size decreases from lanthanum to lutetium ion, the MOH bond strength increases, means due to decrease in size the bond becomes stronger and release of OH minus ion is less. So you can also say that covalent character increases and thus the basic character of hydroxides decreases from lanthanum to lutetium hydroxide. Then another consequence is similarity in second and third transition series, that is 4D and 5D series. There is increase in size when we move in a group from top to bottom, that is from 3D to 4D size increases, but from 4D to 5D the increase in size is not much, and the post lanthanum elements of 5D series are almost similar in size of corresponding elements of 4D series. It is because of lanthanoid contraction that increase in size due to increase in shell from 4D to 5D is compensated by the decrease in size due to lanthanoid contraction. This can be explained by the graph here. As you can see, the three series are shown here. This is 3D series, scandium, titanium onwards. Then 4D series is from yttrium onwards, and 5D series is from lanthanum. Now we can see that the difference in size from 3D to 4D is quite much, but when we see the size difference of 4D and 5D series, you can see the difference is not much between yttrium and lanthanum. And for the next element, that is zirconium and hafnium, the sizes are almost same, also for niobium and tantalum, and also for molybdenum and tungsten. It is because after lanthanum there are 14 lanthanoid elements in which 4f orbital is filled, and due to which lanthanoid contraction occurs due to its poor shielding effect, and size of zirconium becomes less. So the question is also asked in exam, why zirconium and hafnium have similar radii, or niobium, tantalum, or for molybdenum and tungsten they have similar radii. So you have to write the answer only that it is because of lanthanoid contraction. Next is difference between lanthanoids and actinoids. The first difference is about oxidation states. Lanthanoids have generally +3 oxidation state, but they also show +4 and +2 oxidation state, whereas actinoids can show higher oxidation states also. They are more reactive. Why? Because their ionization enthalpies are lesser than that for lanthanoids. Then in lanthanoids all the elements are non-radioactive except promethium, which is radioactive, whereas all the actinoids are radioactive. The magnetic properties of lanthanoids are less complex, whereas those of actinoids are more complex. Another difference is of actinoid and lanthanoid contraction. Actinoid contraction is more as compared to lanthanoid contraction. So this is all about F block elements. Thank you.